Hey guys, welcome. So today what we're going to be doing is going over the process of solving two-dimensional kinematics problems. What I'm going to do to start off, definitely going to start off by sharing the notes. But what I want to do first is I want to just post an example of a 1D kinematics problem that, maybe you can reach back and take a look at this. So this one says change that. A swan on a lake gets airborne by flapping its wings and running on top of the water. The swan must reach a velocity of 6.00 meters per second to take off, and it accelerates from rest at 0.35 meters per second. How far will it travel? And how long does it take? Okay, so this is pretty basic stuff with just a standard kinematics problem. So I encourage you to pause this and work through this just to see if you remember the process without me doing it. So in any event, there's that problem, but I'm gonna go ahead and do it now. All right, so this is fortunately this is not too bad because A and B are basically dealing with the same situation. So what we need to do is we need to look at we need to look for our kinematics quantities. Now delta x, that's something we don't know, and that's what we're asked for in part A, by the way. We can look at V naught. Now, we're not actually told the V naught, but it accelerates from rest. That tells us that the V naught is 0. V final, that's 6.00 meters per second. Then we are given the acceleration, that's 0.350 meters per second squared. And then delta T is also something we're looking for, and we're going to look for that in part B. Okay. Now, as a reminder, the whole goal here is to it's basically to find use a particular equation to basically to find these different quantities. Now, there are a number of different ways you could do this. I'm just going to go through the kind of the way I would look at this one. So I would look at it, this first one, I would say, okay, we have V final, V initial, A, and we're looking for delta X. Well, to me, that says that I want to use this equation. V final squared equals 2A delta X plus V initial squared. Now, that's again not too bad. We can just start plugging in. So it'd be 6.00 squared equals 2 times 0.350 times delta x plus 0 squared. That just goes away. And then when we find this, doing a little bit of multiplication, simplifying a bit, we end up with 36. And I'm gonna stop writing the decimals if I don't need them. I'm just gonna remember that I need to round to three sig figs. And then that's equal to 0.7x. And then I would just delta x, and then I would divide 36 by 0.7. From there, gotta go do that. Whoops, do that in the calculator. And what I get is I get delta x equals 51.4 meters. Okay, so that's what I'm finding with that one. Takes a little while, takes a little distance for him to get off of that. Now for B, once you have your delta x, there are a number of different ways you can do it. Still, I would probably just tend to use the V final equals A delta T plus V initial. And from there, you just end up with 6.00 equals 3.5, or sorry, 0.35. 0.350 delta t plus 0. And then you just find that delta t is equal to 6 divided by 0.35. Go ahead and do that. And we end up with delta t equals 17.1 seconds. Okay, so Swan takes a little bit of time, a little bit of distance to get going, but basically there you go. That's what we're seeing with this problem. Okay, so hopefully this reminded you, this helps you think about what were some of the equations that you needed to use in order to do this. Now, when it gets to looking at the 2D kinematics equations, I'm going to try and elaborate, just articulate what I think the process is, the 2D kinematics problems. And then I'll go over kind of how we do that, and then I'll show you some examples along with some nuance of the way things go. So first thing I want to talk about is the basic process. And the basic process that I want to talk about is uh step one, what you want to do is you want to break your vectors into components. So break vectors, and these are all your kinematics quantity vectors, which is everything but time. Everything but time is a vector. So you want to break it into XY components. This is why we spent a class doing that yesterday, becoming familiar with that, because this is how we analyze kinematics problems. Then the whole idea behind kinematics, and this is something where we're not really going to show, but one of the interesting things about kinematics is that the vertical and the horizontal, the different components, are separable. They basically obey the kinematics equations separately. So what the second step that we're going to do is that we're going to solve the kinematics equations for x, y direction separately. Now, in general, those quantities in the x and y direction are not affected by one another. Now, there is an exception. The delta t quantity should be the same for both directions. And the idea here is that if we're referring to a single event, we can break apart its motion or two events, like a takeoff and a landing, say. We can break its motion up into the x and y components and look at that separately, but the time between those two events is going to be the same for both the x and y components. So there is no x component of time or y component of time. There's just time. Okay, so that's what is going on there. All right, so that's the basic process. Now there will be a little bit of nuance that I'll get into in just a second, but before I do this, I want to give you a sense of, I want to do a quick example, and then I'll talk about then I'll give the details of projectile motion and what we mean by it. So let's just look at this example problem. There we go, and a little bit bigger. And so what we have here is we have a ball is kicked with an initial velocity of 16 meters per second in the horizontal direction and 12 meters per second in the vertical direction. Okay. At what speed does the ball hit the ground? For how long does the ball remain in the air? C, what is the maximum height attained by the ball? Now we'll get into all of this, but what I want to do is I guess we'll do it in like blue. I just want to kind of articulate the process for you. So I'll break this into two pieces. Step one of this process is you want to break all quantities into x and y components. Now, you can do this differently than I do. I'm going to show you my method. It's up to you if you want to do this. But basically what I'm going to do over here is I'm just going to have x direction, and then I'll make another column with y direction. Okay. And from there, what I'll do is I'll just start putting things in there. Now, here is the thing. Do I know the delta x? Now, if we think about what this means, if we're thinking about this soccer ball, what this means, a delta x would be, okay, how far does it go horizontally? How far does it go horizontally when when it's kicked? Okay. And so that's, we don't know that. That's something we don't give. Delta Y. This would be what is the vertical change. Now, it's important to know that it's actually two different events for B and C. You're gonna have a different vertical change for those two events because for B, this is like basically the ball is kicked off the ground, goes into the air, and then lands. For C, the end event that you're looking at is when the ball gets as high as it's going to get. So B and C will be a little bit different. I tell you what, I'm gonna leave out C for now. We'll come back to that when we do things. But delta Y. Now, the reason I want to talk about this delta Y and the reason I exclude C is because if we imagine what has happened here, and sometimes drawing a little picture can help. This ball is kicked and it's going like this. It's going in that kind of shape. Now, we don't know what delta X is. That's why I did this. Delta X, we don't know what that is. But notice, we're on flat ground. So the change in height of this thing, it went up and then it came back down. Now it's horizontally displaced. But basically what's happened is it's the same thing as a ball that got thrown upward and then came back down. Its change in Y, delta Y is 0. So that is something that, is worth knowing. Now, we can have V naught X. Now, this one breaks into components from the get-go, so it's a little easier for us. A horizontal direction had an initial velocity of 12 meters per second. Vertical direction had an initial velocity of 16 meters per second, so little more vertical than horizontal, but nevertheless, that's fun. Now V final. Now, it turns out we don't need V final X and V final Y. It turns out we don't really need to know this. However, one of the interesting things, and you can verify this, is that if your delta Y is 0, then your initial velocity turns out to be equal to your final velocity, or it's actually opposite, because you use the v squared and you basically take the square root. Now you then have to take the negative because it's going in the opposite direction. But it turns out that the y would actually be negative 16. We can verify that. We don't really need to though. So we're not really asked to do anything here. Now I'm going to leave VF sub x alone for a minute, but I am going to erase the question mark because it's something we can actually get very easily if we need it. Now, a lot of times it's not particularly helpful, but the next thing we want to do is we want to say, okay, I'm going to do a sub x and a sub y. And here is the thing. One of this is the thing you need to know about the problem, is that after this thing is kicked, the only thing acting on it is gravity. Okay? The only thing acting on it is gravity, and gravity only pulls in one direction. That's straight down. So gravity is accelerating downward. Now, in this case, that is only the y direction. Now, it's down, so I'm going to say, okay, that's negative g. But when we look at the acceleration in the x direction, there's nothing pushing or pulling on it that's going to accelerate in the x direction. We get into that later in forces. But the idea here is that gravity is the only acceleration this thing has experienced, and gravity is only in the y direction. So A ends up being 0 meters per second squared. And like I said, use negative 10 meters per second squared for G. That's fine. I'm not going to care if that's what gets used. Now, I said we could go back to V final of X, and one of the things to note that if you go to that delta V equals A delta T equation, or V equals A delta T, V final equals A delta T plus V initial. If delta T is not 0, but A is 0, then it turns out V final is just equal to V initial. So in the X direction, and anytime you have 0 acceleration, not squared, then your V final is just going to be equal to your V initial, okay? So that is true for 0 acceleration. And then delta T is something that we're looking for. And delta X is something that we're looking for. Now, here is the thing. What we have here, we kind of sort of have three things in the x equation, or in the x direction, and maybe this is enough to get us in delta x, but it turns out it's not, because the equation we'd use would be the equation we would use would be v final x squared equals 2a delta x plus v initial x squared. Well, notice because a is 0, that term cancels. So this equation turns out to be not very useful for helping us find delta x. So it turns out we need to go to another equation. This happens sometimes when you have zeros for these quantities. So that is what it is. But in any event, and notice that this is true, just 12 squared equals 12 squared, so that's fine. So this equation is not particularly helpful. So typically the way this goes is that your second step, you use one direction to solve for time. Okay. And this is the idea, is that a lot of times in one of the directions, you don't have enough information to get what you want, but you can use the other direction to solve for time. And that's exactly what we can do here. So notice what we have over here is we can find, we can say, okay, delta y equals 1/2 a delta t squared plus v naught y delta t. All right, and these are things we can all plug in to solve for. So 0 equals 1/2 times -10 delta t squared plus 16 delta t. Now, we saw this last in last week's example problems. One of your delta t's is going to be 0. So delta t will be 0. That will be one answer, but the other one will be you have 1/2, or 1/2 times -10 is just -5 delta t plus 16 should equal 0 as well. So that's factoring out a delta t and setting them both equal to 0. And then what you get is delta t equals 16 over 5 seconds, which would be, I think that's 3.20 seconds. Okay, so delta t equals 3.20 seconds. And then our third step is going to be place delta t in both directions. So even though I used the y to solve for this delta t equals 3.20 seconds, I can also put it over in the x direction, 3.20 seconds. Okay, so that's basically what we're going to want to do here. Now, from here, what we can do is we can find our delta x fairly straightforwardly. Now we can use a number of these things. The easiest one, well, actually, I think we might only be able to use one. No, well, yeah. Delta x is going to be equal to 1/2 a sub x delta t squared plus v naught x delta t. Well, notice that this a sub x just goes to 0. That this first term goes to 0. So you get delta x equals v naught x delta t. This is true if there is 0 acceleration. You could also use the average velocity equation for this if you were so inclined. Your average velocity is just equal to your initial velocity because your velocity never changes. So that would work as well. But in any event, what you get here is you get delta x equals 12 times 3.2. And from there, whoops. You get delta x equals 38.4 meters. Okay, so it turns out we ended up solving for both of these. Now, I've always found a kind of interesting thing about this is that you can't really figure it out. You can't really figure out part A unless you figure out part B first. Okay, so the ball remains in the air for 3.2 seconds. And you'd find delta x. Now it turns out, when I'll talk about this, there is a range formula that we can use. We can derive that. I'll show that to you in just a second. But this is but basically we needed to do both of these things if we're going to just use the standard method. Okay. And then the fourth step, which I of course already did, you solve for desired unknowns. All right. And they could be a number of different things. Now, this type of motion is called projectile motion. And the idea behind projectile motion is it has two characteristics. Well, I guess more than two. We could say two characteristics. It's 2D motion and it is in free fall. Okay. Now, what does this mean when we say this? Well, generally what it means is it means that v sub x doesn't v or v naught sub x does not equal 0. V naught sub y does not equal 0. That's typically what we mean by 2D motion. If they were, well, I'll just say v sub y. Sometimes v naught sub y is 0. We'll get into some examples of this, but because there's an acceleration, the object will gain some v sub y. But the free fall, what that means is that a sub y typically just equals negative g, or g if typically we let down be negative in this. That's just most common, but you could let down be positive. It gets a little more confusing that way, but that's what happens. And then a sub x equals 0. Okay, so the idea here is that gravity is the acceleration of the object. If this is what's going on, then we have projectile motion. If there are other accelerations of the object, then it's not projectile motion. Okay. But this is basically the 2D kinematics things we're going to be looking at. Now, this a sub x thing equals 0, that is crucial. That makes your x components significantly simpler, and it makes some things go right. Now, basically, you can have different types of projectile motion. So types of projectile motion. You can just have kind of like the one we already saw. You can have object launched at an angle. Now, I say launched, I just mean projected at an angle on horizontal ground. And again, a basic schematic of this would be something like this. Like that. You can also have an object launched from a ledge. Now, this is you can do this a couple of different ways. The most common way is you launch it horizontally. So what this would be is you would have you would be up here and you would launch your object. You basically shoot it horizontally initially, and then gravity takes over and pulls it downward. But you can also launch at an angle if you're so inclined. When you launch at an angle, it tends to be the problem tends to be a little bit more tricky, but it's not impossible. So basically, this would be, you launch it upward first and then it goes down. I'll try and let's do this. So it would be like that. Okay. So that's basically what you can do here. Now that's kind of both. One of the more difficult ones that I don't think I'm going to put any of these in. I might throw one in as a challenge problem at some point or something. This would be a object lands on a ledge. And these ones do tend to be tricky. The algebra is not only trickier, but the idea here is that not even necessarily on a ledge, but just high up. The idea here is that you launch a projectile and it hits this wall before it comes down. And it could, that looks, but that the way I drew it before, it looked like it hit it at the top. Doesn't need to. It doesn't need to hit it at the top. It can just, hit it at some point during the motion. So this one tends to be a little bit trickier. But nevertheless, these are the kinds of things that can come up. Okay. Now, there are some common types. And this is mostly for the angle, launched at an angle on horizontal ground. The common questions that you get asked are range and maximum height. And I'm going to go through just an algebraic derivation of these. You can use these equations if you want. I definitely suggest working through at least the first few times working through some of these to understand what's going on. But if you're asked for a range equation, basically what you're going to do, and again, I'm just going to do this algebraically. So we have, we're looking for delta x, and this is the thing that we're looking for. The range is delta x, okay? Now, delta y is equal to 0. And again, the reason here is that what we're doing is we're going from horizontal ground to horizontal ground. Okay, so delta y is 0. Now, if this equation I'm going to show you won't work if delta y is 0. So if you're doing this where an object's landing on a ledge, or this where an object is launched from a ledge, this range equation won't work, so you got to be real careful with that. Only works for if you're on horizontal ground. Now, your v initial x, that could be whatever. Your v initial y, that could be whatever. Your v final x, it's important to note that this is just equal to your v initial x, because your acceleration in x is equal to 0. Now, one of the things that your v final y is going to do, that's going to be equal to negative v initial y. We saw this a little bit in the 1D kinematics, that if we threw an object straight up, it basically had the same speed when it came back down. It was just going in the opposite direction. Turns out that's true for the components as well, which makes sense. Okay. A sub y equals negative g. All right. Now, the delta t is basically how we're going to find delta t. What we have is we have delta y is equal to a 1 half, we'll do negative 1 half g delta t squared plus v naught y delta t. Okay, so, and then delta y was 0. So what we can do is we could get 0, and then again, we can divide by delta t. I'll do this. We can factor out delta t. Negative 1 half g delta t plus v naught y. Now, one of the delta t's is 0. That's not the one we're interested in. That's the delta t at the very beginning. We're interested in the one that's not 0. So solving for that, we end up with 0 equals negative 1 half g delta t plus v naught y. Now you can solve for this delta t, and what you end up with is delta t equals 2 v naught y over g. And you can use your unit analysis to kind of show that that's accurate. Then what you do, you take this delta t over here. So 2 v naught y delta or over g. Okay. And then what you know is that delta x is just equal to v naught x delta t. Okay. And again, that's that if your acceleration in the x is 0, then the first term, the 1 half a delta x, 1 half a delta t squared term goes to 0. So this is all you're left with. And so what that means is that delta x, your range, is just equal to v naught x, and we'll multiply the 2, v naught y over g. Okay. Now, if you're given an angle and a speed, then you would need to break those into components before you could do this. Nevertheless, this is the basic idea for range. Now, for height, it's a little bit different. We don't really care about the we don't know what the delta x is. We're not typically asked for that. We're still going to have v naught x that we don't know what that is. Because we're in free fall, v final x is just going to be equal to v naught x. And then a sub x will be 0, and delta t, we don't know, because again, we're dealing with a different time here, which means that the the we can't use the time from the range, because we're not waiting till the thing lands. We want to know exactly at the top. Now, you can make a symmetry argument, and it turns out that this is valid, that the time it takes to get to the top is just half the total time. Turns out that's right. And then your range is just half the total range. That's an argument you can make, but I want to go through this in a little more detail. Now, in this case, it's delta y that we're looking for. This would be the maximum height, by the way. Okay. The delta y is what we're looking for. Now, again, v naught y, this is a variable that we could be given. So we don't know what that is. Now, v final y, this one is important. At maximum height, when I'll do it here. At maximum height, this is basically when the projectile runs out of upward velocity. It stops its upward motion and then changes direction. Now, it's still got horizontal motion, but it stops its upward motion. So your v final y for these cases is actually 0. And that's a key takeaway. Your a sub y is still negative g. And then your delta t, well, we don't know. Okay. So basically what I would do here, you can do this a number of different ways. But probably what I would do is I would find both the delta t and then the y. Now, I think you can do this. You don't really, so this is kind of an interesting case where you don't need the x to do any of this. And it turns out that your maximum height is basically, it can be solved if it's just like a 1D kinematics problem that had whatever initial velocity you were dealing with. So again, we've got enough information to solve all of this stuff now. Because we need to be given v naught y. If you're not given v naught y, then you can't solve this. So we would need to have v naught y, but what we have here is we have delta y equals actually we'll solve delta for delta t first. I think that's easier. We could do this a number of different ways. Well, we can solve for delta y. That's fine. Actually, let's just solve for delta y. So we have v final y squared equals 2a sub y delta y plus v naught y squared. Well, v final y squared was just 0. So we have 0 equals negative 2g delta y plus v naught y squared. Solving for delta y, moving over, we just end up with delta y equals v naught y squared over 2g. And that is the maximum height of these things. And you can go through and you can find the time it takes to get to the maximum height. Turns out the time it takes is exactly half of what we found up here. It's just v naught y over g. And you could kind of see that if you did just the v final equals ay delta t plus v initial problem. But that's what's going on with that one. Okay, so this is basically what we're looking at when it comes to these types of problems. All right, now I wanted to do 1 or 2 more examples and then just give one last piece of advice. So yeah, we'll do definitely one more. All right, so this one is a ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. And then we're asked a bunch of questions about this. So what I would start by doing is I would start by drawing some things that we know. So basically what the diagram we're looking at is something like this. Okay. So we have V naught just horizontally. Now, the thing is, and then we're also told that this is 100 meters and this is 60 meters. Now, if we put our list of two things, so delta x, delta y, v naught x, v naught y, v final x, v final y. Um, and then a sub x, that is always going to be 0. A sub y is going to be negative g, and then delta t and delta t. Those are two things we don't know. Well, we do know a couple of things. One, delta x is 100. Okay, because it tells us that the thing landed 100 meters from the base. V naught x. Okay, well, we don't know what that is. We're not told what it's thrown at. So this is one of the things that we are asked to find. That's what we're asked to find in part B. Okay, so I'll circle that. Just note that we're looking for that. V final x, well, we don't know what that is, but we do know it's going to be equal to V initial x, whatever that is. So we could leave that in. T delta t is one of the things that we're looking for. This was part B, this was part A. Okay, great. Same thing. It's the same delta t. It's a thing to remember. Delta y. People might be tempted to write 60, but just keep in mind that we let down be negative here. So given that, I would say let delta y be negative 60 because it is going down. And these should both be meters, of course. V naught y. Now, this is another one where we're not explicitly given it, but we are told it's thrown horizontally. If it's thrown horizontally, then there's no up or down component. And that means our initial velocity is just 0 meters per second there. Okay, so that's what we're seeing with that one. All right, so keep that in mind. Now, V final Y, this is not what we don't know this. But we can this is what we're going to find in part C. Now, once we find parts B and C, that will basically give us part D. So part D is just kind of a combination of those two. All right, so we need to find the time, the initial x velocity, the initial y velocity. All right, so how are we going to do this? Well, and then I'll just write that as negative 10. Well, I think the easiest way is to just say, okay, what we've got is we got delta y is equal to 1/2 a sub y delta t squared plus v naught y delta t. This is how we can find our delta t for part A. Okay, so part A. Now, delta y was negative 60 equals 1/2 times negative 10 delta t squared, and then plus 0 delta t. So this is cool. That term just goes away. And then solving for this, what we can do is we would end up having negative 60 equals negative 5 delta t squared. So dividing that by 5, we're going to get 12 equals delta t squared. And then delta t is just going to be equal to the square root of 12. This one, it actually does 4 significant figures in the problem initially, looking back up at that. So 100.0. Actually only 3 because the 60 only gives us 3. So this is another case where looking at 3 sig figs will be fine. So I'm just going to take the square root of 12, which is 3.46, 3 significant figs, and that would be fine. So 3.46 seconds. Now we could use that for part, and we are actually going to need to use that for part B. So 3.46 seconds. And the idea here is that delta x is just going to be equal to v naught x delta t. Again, remembering that's that delta x acceleration equation, but because the acceleration is 0, that first term vanishes. So what we have here is v naught x is just delta x over delta t. And from there, it's kind of no problem because we have delta x was 100 meters. So 100 meters divided by 3.46 seconds. So there we go. And from there, we end up with 28.9 meters per second for this. Okay, so that would be part B. Now, part C, we can, we can do this a number of different ways. I think the easiest way is to just say V final y squared equals 2ay delta y plus V initial y squared. I like this because it just that V naught y term just goes to 0. And then we just end up with V final y, and I am going to take the square root, doing a little bit of algebra and substitution at this time, but it'll be 2 times -10 times -60. So what we get there is the square root of 1200, and that's just going to be 34.6. So very similar to what we saw up above. 34.6 meters per second. Okay, so that is all we've got for that one. And what we can do now is we can just say, okay, then our velocity vector, V final vector, is just going to be 28.9 meters per second. And oh, here's the thing. This is something that I did forget. When we take the square root, we have to know that it's plus or minus. So it's plus or minus 34.6 seconds. And then we have to make a physical judgment about which one we want. Do we want the positive or the negative? Well, if we look back at our situation, it's going downward, and we know we've already defined down as negative. So we're going to have negative 34.6 meters per second. I almost made that mistake. Very important to catch those. So we choose this because the object is going down. All right. And so it would be negative 34.6 meters per second. And that would be part D right there. Okay. One last thing I want to talk about is just this. It's more a rule of, it's not really a rule you have to, well, you should follow it, but it's you'll notice that this is a common sort of art that we do when we set up problems. And I'm just going to put it this way: choose axes such that one of your accelerations is 0. Okay, so here's an example of that. This is a two-dimensional kinematics problem. It's not free fall because it's on a ramp. Now let's just say we're on this ramp and we've got a block sliding down, and we are told that this thing accelerates down the ramp 1.00 meters per second squared. And let's say we're told that theta equals, we'll just say 45 degrees. And then this equals 1 meter. Now, you might be able to see that this is going to be that you can boil this down into a 1D kinematics problem. But here's the thing: don't be tempted to set up your XY like this. Because if you set up your Y and your X normally, what you'll have is you'll have an acceleration that is like this. So you have an acceleration in that direction. So a sub x will not be equal to 0, and a sub y will not be equal to 0. This is not helpful. Doesn't come up in this chapter, but it will come up when we start analyzing forces. It is very unhelpful to have accelerations in both directions. And the point is, what you can do instead is you can basically rotate this and set up an XY coordinate system that looks like this, where X is in the plane of the ramp and Y is just perpendicular to that. If you do it that way, what you do is you now have, and again, you can set up coordinate systems however you want. But what you now have is you have a sub y equals 0. And that is what's useful. And the whole point is that it's only accelerating in this blue axis that I've drawn, it's only accelerating in the x direction. And then we can say, oh, a sub x is then equal to 1 meter per second squared. And the whole point of this drastically simplifies the kinematics equations. If you have one of your kinematics accelerations be zero, you noticed that when it was free fall, it was the a sub x that was zero. So that became a lot easier. In this case, it's the a sub y is zero, but it's going to make the kinematics in the y direction very easy because again, you're not going to have any change in the velocity in that y direction. Okay. And the point is that even though this thing is speeding up and it is kind of going down and horizontally, if instead we think about the situation as being in the plane of the ramp and perpendicular to the ramp, it never accelerates or changes its speed relative to the perpendicular of the ramp. It's always just going in the plane of the ramp. Okay, so this thing just becomes a lot easier. You can solve it that way. This will come up a lot more in the chapter on forces. So I just wanted to give you a heads up and note that this is something that we're going to be able to do. Okay, but with that, I'm gonna call it good there, and thank you all for joining me, and I will see you in the next lecture.